Alright guys, welcome back. We're going to be solving another question from the second chapter of the Meriam textbook in geomechanics. And in this one we have an exerciser that begins with his arm in a relaxed vertical position OA, at which the elastic band is on a stretch. So by the time that we have his arm at this position, we have the initial length, which we know is what we have for AC, or 740 millimeter, or 0.74 meter. So we have the unstretched length of the elastic band, and then he rotates his arm to the horizontal position OB, and we also know the elastic modulus of the band is 60 Newton per meter, meaning that a force of 60 Newton is required to stretch the band for each additional meter of elongation. So based on the elastic modulus, we should be able to find the force as long as we have the elongation. And the question is asking for the moment about point O of this force F that we have, that the band exerts on the hand at point E. So we have the force F, and if we want to find the force, as I mentioned, we have something very similar to what we have in the spring, K, or the constant times displacement. And for finding the X, we have to find the stretch leg, when we can call it L minus L0, which is the unstretched length, where we found that L0 is actually 0.474 meter, which is the 740 millimeter that we have. And for finding the stretch part, we have this right triangle in here, which I'm going to bring it here. So we have the sides of this right triangle. We know this is 635 millimeter. If we want to find the other side, we basically have the length of the arm, which is 635 again, plus AC, which was 740. And with a simple Pythagorean theorem, we can find our L, or the stretched length of the band. So let's do that. Let's do the Pythagorean theorem. L is equal to square root of 635 squared plus 635 plus 740 squared. So let's calculate this. So this is going to give us 1514.55 millimeter. Now we should be able to find the force. We have the elastic modulus of the band, which is 60 Newton per meter. That means we have to use all of our dimensions based on meter. So we have L0, and the stretch length, which was 1.51455 minus 0.74, and this will be in meter unit, so we're going to get the force in the Newton, and we're going to subtract that by 740 divided by 1000 times 60, and this will be our force, 46.47 newtons. So now that we have the force, if we want to find the moment, so we are trying to find a moment about point O, and this is our force F. And if we dissolve these two forces into two different components, one parallel to horizontal and one perpendicular to that, only the vertical component is going to make a moment, and as we can see, it will be in this direction, so it will be a counterclockwise moment. But before that, we need to figure out this angle here and call it theta, and that shouldn't be hard too. If we just find the cosine of theta, we basically have 635 over the hypotenuse, 1514.55. So our theta would be cosine inverse of 635 divided by 1514.55. So the angle will be, so we just have 635 over 1514.55. And this is going to give us 65.2. And now we should be able to find the moment, counterclockwise positive as always. And as we can see, the moment is counterclockwise, so positive. We can figure out the force, 46.47. That's our F, but we are looking for the vertical component, which would be the sine of theta, so sine of 65.2 degrees, and that would be the F part of our moment. And if we want to find the R, we basically have distance from here to here, which is 635, again divided by 1000 to get it in meter, and that should give us the moment in Newton meter. So let's calculate this. 46.47 times sine of 65.2 times 0.6. And that's going to be the final answer, 26.79 Newton meter. And as I mentioned, the moment is going to be counterclockwise. Hope everything was clear. Let me know if you guys have any questions, and you guys take care. I'll see you in the next video. Have a good one.